I am Brendan Hill, and I work with Nazia Mazaffar and Salwan Daman at NIWC Pacific. Our presentation and paper is a comparison of techniques for non-data aided carrier tracking of phase modulated signals. This hypothetical example illustrates the problem we're trying to solve. Imagine there's a satellite at a 500-mile altitude, and it is a relay in a 2.45 gigahertz communication channel. Based on its position and altitude, it's going to have to travel fast in order to maintain orbit, and the observed Doppler as it flies overhead is going to have a magnitude of about 57 kilohertz maximum, and when it's right overhead, it's going to have a maximum Doppler change of minus 550 hertz per second. The satellite's only overhead for about 14.5 minutes, and it's not going to come around again for almost 2 hours. We'd like to use as much of that overflight time to do data transfers, especially if we want to communicate between two ground terminals that are within view of the satellite but not within view of each other. The problem is those ground terminals might have been designed without those large Doppler offsets associated with fast-moving LEO craft in mind. So what we'd like to do is have a technique for detecting and tracking a time-varying Doppler resident on the satellite that doesn't require demodulating the signal. One way to do this is to locate a pair of filters called band edge filters, one at the positive and one at the negative ends of the modulated channel. If we know the modulation rate and we know the roll-off factor in the shaping filter, then the optimum choice for the band edge filter coefficients is such that the frequency response is equal to the derivative of the shaping filter's frequency response. As the roll-off factor increases from 0 to 1, the band edge filter locations also change because the edges of the shaping filter change. In addition to their locations, the band edge filter bandwidths themselves also increase as the roll-off factor increases. And this underscores the fact that they're really operating on the excess bandwidth of the signal. The strategy that we're going to use with the band edge filters is when a signal of interest has a Doppler on it, one of the band edge filters is going to have more energy than the other, and that energy difference will tell us what that Doppler offset is. This block diagram shows how to use band edge filters in a frequency locked loop structure. A way to measure the energy difference between the upper and lower band edge filters is to take the sum of the band edge filter outputs and multiply it by the complex conjugate of the difference of the band edge filter outputs. The real part of this product has an interesting spectrum. There should be a large spike located at 0 hertz, and its size is proportional to the frequency offset of the signal of interest. So our error term is then passed through a proportional integral filter, which gives us a frequency update that we feed to a numerically controlled oscillator. The output of the numerically controlled oscillator at this point is a phase, so we convert it to a sine and cosine term with a complex exponential, which is achieved with a lookup table. And if we take the conjugate of that and multiply that by our incoming signal, then we will effectively cancel out the Doppler of the incoming signal if we are in a state of lock. How well does the band edge FLL perform? The two main things we're worried about are how quickly does it lock on to the frequency change and what's the frequency error after it locks. I've got two scenarios here. They're both operating off of a 50 kilohertz BPSK signal that has an initial Doppler at 12.5 kilohertz and a Doppler that changes with time at a rate of minus 550 hertz per second. Here on the left, it's 20 dB, and here on the right, it's a 5 dB. The spectra on the bottom show what the matched filter, showing the Doppler offset, the band edge filters, and this figure of merit that we talked about, the product of the sum of the band edge filter outputs times the conjugate of the difference, and the real part of that showing the spike there at DC, which is proportional to the frequency offset. So we get a very fast locking time with this, but in the 5 dB SNR case, our standard deviation of frequency error gets worse, as one would expect. If we wanted to change that or improve that, we would have to make a trade between our ability to lock quickly. So we would be changing these loop parameters, the damping factor zeta or the loop bandwidth eta, in order to improve that. Band edge filter frequency lock loops don't work very well when the Doppler is so large that it exceeds the modulation bandwidth of the signal of interest. I've changed the scenario so that now I've got a 10 kilohertz BPSK signal, and I'm still operating at 20 samples per symbol, so now I'm at 200 kilosamples per symbol for the actual sample rate. And I'm operating at 20 dB for both of these sets of curves that I'm showing here. On the left, I've got a 30 kilohertz offset. And you can see that the upper band edge filter and the lower band edge filter are only being excited by noise. It's only in the side lobes that we actually get any relevant energy from the signal of interest. And the difference between them is so small you can hardly tell which is which. And for that reason, there's no locking action on this. 20 seconds elapse and the FLL never achieves lock. But in this scenario on the right, I changed the Doppler to be such that it just starts to excite the side lobes of the upper band edge filter. So now there's an appreciable difference you can see graphically between the upper band edge filter and lower band edge filter, and it's just enough to pull it in ever so slowly until it pulls in some of the energy into the main lobe of the upper band edge filter, and then it kicks in and quickly operates and locks onto the signal. If we replace the band edge filters with half band filters, then we actually get the ability to track large Doppler offsets. So if I rerun that scenario using half band filters instead of the optimum band edge filters, now all of a sudden I can lock onto that offset in less than 30 milliseconds, and I've got a very low standard deviation of error. But we have to be careful. We have to judge how effective the half band filters are in place of the optimum filters in the scenario where the Doppler is within the modulation bandwidth. So I reran the scenario where the Doppler starts at 12.5 kilohertz and changes by minus 550 hertz per second. And I see that it has a similar locking time, but the standard deviation of the error is significantly worse. And that makes sense because the optimum filters are designed to minimize that error. So what we could do is numerically add the optimum band edge filter coefficients to the half band filter coefficients. And that's one way we can get the best of both worlds. If we rerun the scenario where our Doppler is just 12.5 kilohertz for a 50 kilohertz modulated signal, we can achieve lock and we still have a pretty low standard deviation of frequency error. It's not quite as low as it was when it was just the optimum filter coefficients by themselves. But then if we rerun the scenario where we had a 10 kilohertz modulation bandwidth and a 30 kilohertz initial offset, and this time if we turn on our Doppler change to minus 550 hertz per second, this time we're still able to lock onto it and track very accurately. And you see this kink that happens in the curve. This slope here occurs during the period of time when the half-band filters are in effect, and once we push the signal of interest into the bandwidth of either of the band edge filters, then it speeds up. Another device we can use to measure Doppler is a pre-filter delay multiply device. We have a noise-reducing filter, which converts S of t to C of t, and we just multiply the signal times a delayed version of itself. As long as this delay is between 0 and 1 symbols, the output spectrum of B of t is going to consist of spectral lines showing the modulation rate and possibly integer multiples of those, depending on what shaping filter was used to make S of t, and it will be located at twice the Doppler frequency in a situation where S of t is a BPSK signal. The appearance of the spectrum of the output of a delay multiply device is affected in part by the shaping filter used in the transmitter and is also affected by the actual delay. If we have a rectangular shaping filter in the transmitter and we don't have any delay, then all we're doing is we're squaring the device. And for BPSK, plus ones and minus ones both square to 1, so we only have a tone at twice the Doppler rate. But as soon as we have some delay, we start to see the spectral lines associated with the symbol rate. As we increase our delay, though, you'll notice that the spectral line associated with twice the Doppler starts to get de-accentuated. Something similar happens if we had a raised cosine shaping filter in the transmitter. Here, without a delay, we still see the spectral lines associated with the symbol rate because of our non-zero value for the roll-off factor. If alpha had been 0, we wouldn't see them there. But as we increase the delay, the spectral line associated with twice the Doppler disappears. The pre-filtered delay multiply FLL structure is very similar to the band edge FLL structure. Here's our pre-filtered delay multiply element, and these parts over here just let us measure the phase change between two adjacent samples. The phase change versus time is frequency, so the rest of this system is very much like the band edge FLL. Now we make a comparison to the performance of the delay multiply FLL in high and low SNR environments. The first thing we had to notice is that we had to change our damping factor and loop bandwidth parameters. They don't work quite the same in the delay multiply FLL as they did in the band edge, because the band edge was operating with an error term related to an energy difference. And in this case, the error term is an actual direct measurement of what a frequency is. So in this scenario here, we had to find a set of damping factor and loop bandwidth parameters that gave us a comparable locking time as we had with the band edge filter case. And we see that we have a very noticeable degradation in the standard deviation of the error in both high and low SNR when we make a comparison to what they were for the optimum band edge filter solutions. A frequency lock loop built out of a pre-filtered delay multiply device is able to track a BPSK signal which has a Doppler offset of up to plus or minus a quarter sample rate. And here's a scenario where we've done that. A 50 kilohertz BPSK signal of interest with a 250 kilohertz initial Doppler changing at minus 550 hertz per second. We're able to lock onto it within 12.2 milliseconds, but our standard deviation of error after that is over a kilohertz. If we wanted to lower the standard deviation of error, we'd have to trade our loop control variables and live with a longer locking time. So what we found is that overall, optimum band edge filter frequency lock loops provide the best combination of lock time and frequency error. We're able to lock on within milliseconds. We're able to keep the standard deviation of frequency error after lock to a minimum. And this is especially true when we're within the modulation bandwidth of the signal of interest. We're able to work with band edge filters' limitations in their inability to detect and track large Doppler offsets by making a hybrid optimum plus half band filter that takes care of the scenarios where the optimum filters don't work so well. But the pre-filter delay multiply frequency lock loop is a viable alternative because a complicated design involving band edge filters is going to use a lot of filter coefficients. There's the upper and lower band edge filters, which might need a lot of coefficients to faithfully represent and operate on the signal of interest that you want to track. But the pre-filter delay multiply FLL only has one filter, and it's the noise reducing filter, which could be reduced in complexity if you're interested in saving space or logic elements in your field programmable gate array. These are the references that we used in our paper and our presentation for band edge filters and pre-filter delay multiply devices. Thank you for listening.